Yeah. I don't have any content about it, but I want to make sure I'm relaxing for a little bit. Gives the it's still use that or you do partial functioning like like either like finding like you're finding the yeah. I think it's really and it's really getting at it's so complex. Oh, is the workshop two doing survey and then like on Tuesday? Workshop, right? Yeah, like what? To the yeah, I guess we'll see what happens. We have the one on the Sunday. This one was checking. I sent you that solution. Yes, I might confuse and please. I don't see if I can do anything, but. Yeah, but I still got like an hour or two. I'm just gonna chill out of the time. Or do you? Or do you?
Thank you. Good, yeah, so we can, so we do not, we had to decide on what. For electric. I did like. Although it is, although it is. What is it? I think it's even.
Okay.
I.
No.
Yes.
Perfect, thanks. I can look.
Appreciate. That's very.
Bring February next to the office.
Thank you. I want to tell someone to see.
And I'm calling for spirit.
Dude, you know, he records the lecture. He posts it. That's the trend. You post the lectures, right?
Yeah.
Yeah.
Sometime the middle late. I think I posted the one from Tuesday.
Okay. My event is having to leave right now. So
Oh,
the
really?
Education parks.
Oh, okay. Okay, yeah. I mean, the lectures will be on later, so.
He literally just gave you an appointment.
Food, the lectures are forever, but food only comes out once, right?
Free food.
Oh,
This one is actually.
like almost no problem too. We can ask a question.
Said what?
So.
All right, it's 4 o'clock. Let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? Doing okay?
no longer hell on earth, and so it's okay to go outside now, so that's good. Yeah, my plants have been kind of dying the last the last few days, and so I'm glad that the heat wave is over for now. What we can do. Okay, so the plan for today, we're just going to pick up where we left off on Tuesday. So we were kind of in the middle of an example, multivariable optimization using classical methods. So we'll go ahead and finish that up. I have one more example from that section as well, just to give you another idea of how those methods work. And then we'll move on to constrained optimization. So my plan, hopefully today, we'll get done with the first method called direct substitution. And then we'll move on to other methods. Okay, so some announcements. So homework problem set 1 was due on Tuesday night. Homework 2 is basically ready for you guys. I just have to just do some last minute formatting. So I'm going to post that on Canvas when I get back to my office today. Homework 2 is all about classical methods, and so up until this point, we'll probably be able to do half of it. And so the half that you can do is all the unconstrained stuff. So that's problems. Problem 1 is the conceptual question, so you'll do half of that, and then problem 2, problem 3. Problems 4 and 5, we'll work on that over the next couple of weeks. And then it's going to be due. It is a much longer assignment, so it's going to be due about 2 weeks from next Tuesday. Yeah, so quite a while for you guys, but it's a big one, so you want to make sure that you're working on it throughout those 2 weeks. Okay. All right, any questions I can answer before we get started for today? Okay, all right, so let's go ahead and pick up where we left off. So actually, let me just scroll up here so we can look back at the example that we're doing. So just to kind of refresh your memory, the example that we were discussing is we were looking at this situation with 2 carts that were supported by 3 springs. And so we're pulling on this entire system here with the tensile force P. And what we were solving for here is the equilibrium positions x1, x2 of the 2 carts. Okay. And so what we were saying is that, even though this is technically just a mechanics problem, we're formulating it as an optimization problem because, whenever you have a system in equilibrium like this, it's always, the equilibrium position that is always obtained by the system is always the one where the potential energy is minimized. Okay. And so what we did was we wrote out a formula here for the potential energy of the entire system, which is comprised of the potential energy of the 3 springs along with the work done by the force. Okay. And then we are using our classical methods to minimize this equation relative to the positions x2 and x1. Okay. So we have a very kind of classical kind of 2D optimization here, 2 design variables, and so we have to use our classical methods, taking derivatives, computing Hessian. So we did the first part of that last week. So what we did was we took partial derivatives of our objective function with respect to our 2 design variables, partial u, partial x1, partial u, partial x2. Okay, what that gave us was a system of 2 equations for our 2 unknowns. And so the last thing that we did was we solved those 2 equations for our design variables. Okay. And so what we found was that x1, the position of cart 1, is equal to p times k3 divided by quantity k1 times k2 plus k1 times k3 plus k2 times k3. And then x2, very similar, is p2 or p multiplied by k2 plus k3 divided by the same denominator as above. Okay. And so these two values here for x1 and x2, these are the solution to our optimization problem. Okay. And so the next step that we have to do here is that we need to determine if these 2 points here represent a minima in our objective function. And to do that, we need to go towards the to do the next step in our procedure, which is computing the Hessian. All right, so let's go ahead and do that. Okay, so in this step here, we compute the Hessian. And determine. So what we need to do is we need to take our Hessian and determine if it's positive definite. If it's positive definite, then we have a minimum. Okay. Okay. So let me start with this. Let me rewrite the first partial derivatives. Okay, partial u partial x1. This is equal to k2 x1 minus k3 x2 minus x1. And we have the first partial derivative with respect to x2. K1 x2 plus k3 x2 minus x1 minus p. Okay, so this is our starting point, because in order to compute the Hessian, we need, remember the Hessian is a square matrix of all the second order partial derivatives. Okay. So let's compute all the partial derivatives, or second order partial derivatives. All right, so let's start with the first one. So let's do partial squared u partial x1 squared. Okay. We're going to take the first equation that we have at the top there and just take the derivative with respect to x1 one more time. And so we take the derivative of that with respect to x1, we get k2 plus. So we have a minus k3. Okay. Derivative of that inside part of x2 minus x1 with respect to x1 is just going to be a minus. And so partial squared u partial x1 is k2 plus k3. Okay. Now let's take the second order derivative of the second derivative. Okay, so with respect to x2, we have partial squared u partial x2 squared. So we're just taking the derivative of the expression at the top with respect to x2. So that gives us a positive k1 plus positive k3. And that's it. Okay. Nothing else depends on x2. And you take the derivative of the p is just a constant. And so that's just going to go to 0. Okay. Well, we need one more derivative here, and so that's the cross derivative. Okay. And so the cross derivative is partial squared u partial x1 partial x2. Okay. Now it doesn't really matter which order that you take this, right? And so the thing with the cross derivatives is that the order is kind of interchangeable. And so you just want to make sure that you do the opposite one. Okay. And so the way I'm going to do this is I'm going to take this expression. So this expression at the top here, we've already taken the derivative of the objective function with respect to x2, okay? And so in order to get this, we're going to take that expression and then take the derivative with respect to x1. Okay. Now, the other way you could have done this is you could have gone from the first one here. And so this quantity that I just circled at the top, we've already taken the derivative with respect to x1. And so to obtain the cross derivative from here, you just do the opposite. So you take the derivative with respect to x2. Okay, you'll get the exact same thing. And so it doesn't really matter which order that you do. Okay. Okay. So let's take the derivative of this guy with respect to x1. And you're going to see that most terms actually cancel out. And so the only term that we have is just a minus k3. And you can verify that too. You can verify that we get the same thing. And so we come back up to partial u partial x1. If we take the derivative of that with respect to x2, you can kind of just see very quickly just by inspection that you're just going to get a minus k3 as well. Okay. So for the cross derivative, you know, it doesn't matter which order that you take the derivatives in, as long as you do one first and then the other one after. Okay. And then on the off chance they do a 3D, a three-dimensional problem, you know, you're gonna have more than one cross derivative in that case. Again, you know, the order doesn't matter. You just have to make sure that all the derivatives are okay. And so using these results, let me go ahead and circle them all just to make them a bit more clear. We can use these results to form our Hessian matrix. So for a two-dimensional case, we have a two by two Hessian matrix. So you have partial squared u, partial x1 squared, partial squared u, partial x1, partial x2, partial squared u, x1, partial x2, partial squared u, partial x2. All right, so generally the form of the Hessian is that we have on the main diagonal, and so starting from the top left corner and going down, that's all of the double derivatives. Okay, so that's the derivatives with respect to the same you know, design variable, and then everything on the off diagonal, those are going to be all your cross. Okay, so let's just go ahead and plug in what we found up here. And so plugging in the results that we just found in the top left, we have K2 plus K3. Minus K3, K3, K1 plus K3. Any questions on how we obtained this result so far? Okay, good. All right, so now that we have the Hessian matrix, the next step is we need to see if this matrix is positive definite. And so if you remember from last time, you know, the way to determine if a square matrix is positive definite is we need to check the determinants of all of the principal submatrices. If all of these determinants are all positive, if all those principal submatrices are all positive, then our Hessian matrix here is going to be positive definite. Okay. So what are the principal submatrices again? Remember, you're going to start from the upper left-hand corner and then just kind of make, you know, kind of imagine you're kind of taking a square and you're kind of dragging in Microsoft Word and you're kind of dragging the corner downward to make it bigger. Okay. So the first principal submatrix is just the top left term right here. We'll call this A1. So we're off to a great start. And so A1 you can see is positive. So the derivative of just a number is just the number itself. So you know, we're off to a good start. And then what we're gonna do is we're gonna grab this corner right here and kind of drag it downwards to get our second principal submatrix. Okay. And so our second principal submatrix is just for a 2 by 2 is just the entire matrix. Okay. So we need to compute the determinant of this matrix. We'll go ahead and do that. We're going to get the determinant of A2. Okay. And so if you remember how to compute the determinant of a 2 by 2 matrix, you're going to multiply together the two terms on the main diagonal, okay? Right, and sure, we're gonna multiply K1 plus K3 multiplied by K1, or K2 times K3. Okay. K2 plus K3, right, K1 plus K3. So that's the product of the top left term in the matrix and the top and the bottom right term in the matrix. And then from this, you're going to subtract the product of the two off diagonal terms. Okay, in this case, they're exactly the same. We're going to take the minus K3 times minus K3. Okay. And so ideally, this should be a positive number. Okay. All right, so let's go ahead and FOIL this out. And so if you distribute the first two terms out, we get K2 K1 plus K2 K3 plus K3 K1 plus K3 squared. Okay. So everything in the parentheses there is just the FOIL, or just the distribution of those two. And then the last term there, we're just going to multiply together. So we have a minus of a minus K3 times a minus K3. Those last two negatives are going to cancel out, and so we just have a minus K3 squared. Okay. And so from here, we can kind of easily see that this is also going to be positive, right? Because we see, even though we have a negative term here, right? For the most part, all of our terms here are positive, but we do have that one negative. But that one negative is going to cancel out with this term right here. You have two identical terms, they're just going to cancel out. And so all we're left with is K2 K1 plus K2 K3 plus K1 K. And since remember what these K's represent, all of these K values here are just spring constants for the springs, right? Just by nature of being a physical property, they're all the K's here are going to be a positive number. It doesn't make any sense for a spring to have a negative spring constant. And so since all the K's are positive, then this quantity is also going to be. Right, and so that's it for this example. And so because the determinants of both the principal submatrices, both A1 and A2 are both positive, then our Hessian matrix is therefore a positive definite. And so what that means is that our computed optimal point, so our computed values for x1, x2, that represents a minima in the system. All right, any questions on this example here? Okay. All right, and so that's multivariable optimization. So it is a bit lengthy. It kind of took us the last 15 minutes of the last lecture and the first 20 minutes of this lecture. So these problems do get long. And this is just even going just up one variable, right? And so if you have a three-dimensional optimization, you can imagine that the amount of work is going to grow by a lot. Okay? And that's generally the theme with optimization in general, is that, yes, it is possible to do multivariable optimization. In fact, most of the interesting problems out there are multivariable, but you want to be really careful with adding more variables to your problem. Once you start to get up to, over 10 variables, even the most sophisticated algorithms are going to struggle. Okay. So when we get to the end of the class, and what I mean by the end of the semester, we'll have kind of a more formal discussion of, how do you even determine the design variables? How do you choose which ones are going to be, the ones you're going to optimize over and which ones you want to fix? Okay, so there's a little bit of philosophy. Okay, let's do one more example before we move on to constrained optimization. Because the thing with these with just optimization in general, the more practice that you get, or the more problems that you get exposed to, you kind of build more into it. So I kind of designed this class with a lot of examples to kind of show you guys how these problems work. Okay, so let's do another two-dimensional optimization. This one doesn't have a fancy story or a fancy figure that goes along with it. It's kind of just purely a math problem. So I'm just going to give you the objective function. And so our objective function in this case is a function of two variables, x1, x2. If x1 cubed plus x2 squared, or excuse me, x2 cubed as well. Plus 2x1 squared plus 4x2 squared plus 6. All right, and so what we want to do here is we want to compute all of the extrema in this objective function. And characterize them as either a max, a min, or a settle. All right, so pretty straightforward problem. So let's just go ahead and get started, right? So the first step that we need to do is we need to take the first order partial derivatives, right, and set them equal to 0. All right, so we have partial x1. We'll take the partial derivative of that objective function with respect to x1. Okay. All right, so if we do that, we get 3x1 squared plus 4x1 to 0. All right, we have an interesting objective function here, and so if you'll notice that all of the terms in this objective function are completely kind of decoupled from each other. So we don't have any terms that involve both x1, x2. Okay? And so when we take the partial derivative with respect to x1, what we get is a function of just x1. Okay? Now I did this for this problem just to kind of make it convenient, just to make it a little bit fast, so we don't have to solve a system of equations. But it's just something I kind of wanted to highlight. But this is not always going to be the case. Okay. So since this equation only involves x1, we can solve this for the values of x1 right away. Okay. And so, first thing you should notice that, we have a quadratic function here, so we're gonna get multiple solutions for x1. Okay. So let's factor out x1 from this quantity here. And so we factor out x1. Okay. Because both 3x1 squared and 4x1 have a common factor of x1, so we can factor that out. And so we factor out x1, and we get 3x1 plus 4. And that equals to 0. Okay. So from here, we can kind of easily solve for the values of x1 that satisfy this equation. Kind of enough because we have kind of a very simple expression in that equals 0, right? And so when you have two quantities multiplied by each other and they equal 0, there's two ways to make that happen. You can either have the first quantity equal to 0 or the second quantity equal to 0. Okay. And so our first quantity here is very simple, it's just x1. And so the only way to get the quantity x1 to be equal to 0 is to set x1 equal to 0. Okay, so that's our first solution. The other way to get this equation to equal 0 is to set the second part equal to 0. We have 3x1 plus 4 is equal to 0. We solve for x1 here, we get x1 is equal to. So I'm going to subtract 4 from both sides and divide by 3. So we get x1 is equal to minus 4 over 3. Okay. Now let's do the same thing for x2. Okay. So let me come back up to the objective function here. And so we're going to take the derivative of that with respect to x2. Okay. And so we have partial f of x2. So if we do that, we get 3x2 squared plus 8x2 equal to 0. Okay. We can do the exact same thing with this one. So if we have a quadratic function, so we can factor out x2. And once again, we get two solutions for x2 from this equation. Okay. So one way that we can make this equation 0 is if x2 is simply equal to 0. The other way to make this this equation equal to 0 is to set that second part equal to 0. So we have 3x2 plus 8, 0. So once again, we can solve this equation for x2. So I'm going to subtract 8 from both sides, divide by 3. X2 is equal to minus 8 over 3. Okay. So from this analysis, or so from the classical methods here, we have two possible combinations for the extrema for both design variables. Okay. And so that kind of begs the question of, which one of these is the optimal point? Well, technically all of them can be, right? And so in this case, we have 4 optimal points because we need to take every possible combination of these solutions. And so that means that we have 4 optimal points to check here. Okay. All right, so our 4 possible points are x1 is equal to 0, x2 equal to 0. Okay. That's our first possible combination. So the second possible combination is x1 is equal to 0, and then x2 is equal to -8/3. Our next possible combination is x1 is equal to -4/3, x2 is equal to 0. And then our final possible combination is -4/3. X2 is equal to -8. All right, so all of those are possible extrema, or in other words, those are places where the derivative of our objective function is equal to 0 in both variables. Okay, so we need to check every single one of these because we don't know, which of these are minima, which of these are maxima, or maybe none of them are minima or maxima at all. Okay, so from here we need to check the Hessian at each and every one of these points. Okay, any questions on how we got to this point here? Okay, cool. All right, so let's go ahead and compute the Hessian. All right, so now that we have all of our extrema, we we need the Hessian before we can continue. So let's go ahead and take the second order derivatives. All right, so let's take partial squared f partial x1 squared. So take the derivative of this guy again with respect to x1. And so that's 6 x1 plus 4. Let's take the derivative of the objective function twice with respect to x2. Okay. We do that, we get 6 x2 plus 8. And finally, we have the cross derivative, partial squared f of x1 partial x2. Once again, it doesn't matter which direction that you go. You can take the derivative with respect to x1 first, then x2, or you can take the derivative with respect to x2 first and then x1. Okay. You're going to end up with the same result, and that result in this case is 0. So because, remember I mentioned earlier that each of the first partial derivatives, they're only functions of single variables. And so when you take the derivative with respect to the other design variable, you're just going to get 0. Okay. So that makes our life easier, and so it simplifies our Hessian quite a bit because we know on the off diagonals it's just going to be. Okay. But unlike the previous example, and so if you remember from the previous example, our Hessian matrix was all constants, right? It was all just K2 or Ks, right? And so for the first time, we have a Hessian matrix here that actually depends on our design variables. So you can see we have x1 and x2 present here in these second order derivatives, right? And so what that tells us is that the value of the Hessian is going to change depending on what we plug in for x1 and x2 in this case. All right, so let's go ahead and form the Hessian matrix then. Okay, so our Hessian matrix in this case is 6x1 plus 4. And we have zeros on the off diagonal. And in the bottom right, we have 6x2 plus 8. Good. Let's write out the expressions for the principal matrix or principal submatrix determinants. Okay. We can't compute them yet without plugging in values for x1, x2, but let's just solve for those expressions. All right, so remember the first principal submatrix is simply just the top left entry. We have A1 is equal to 6x1 plus 4. And the second principal submatrix is A2. Okay, that's just the entire matrix. So let's go ahead and take the determinant of A2. Is equal to quantity 6x1 plus 4 multiplied by quantity 6x2 plus 8. And then when we subtract the off diagonals, we just get minus 0 times 0, and so it's just 0. Okay. Okay. So let's evaluate this at each extreme. So we have 4 points to check this at. So we have 0, 0, we have 0, minus 8 over 3, minus 4 over 3, 0, and then minus 4 over 3, minus 8 over 3. Okay, so let's start with the first one. So our first extrema was x1 is equal to 0 and x2 is equal to 0. So let's plug those into our values for a1, a2. For a1 we get 6 times 0 plus 4. That's equal to 4. Okay. And our determinant 2, we have quantity 6 times 0 plus 4, quantity 6 times 0 plus 8. And so of course, all the terms multiplied by 0 are just going to equal 0. And so we just get 4 times 8, which is a positive 32. And so the determinant of our first principal submatrix is positive. Determinant of the second principal submatrix is also positive. And so this is basically the same situation we had as our first example. So at 0, 0, Hessian is positive definite. So this point is a minimum. Okay, let's evaluate the second point now. So our second extrema is x1 is equal to 0, x2 is equal to minus 8 over 3. Okay. So at this point, let's evaluate A1. A1, once again, is 6 times 0 plus 4, equal to positive 4. And let's compute the determinant of A2. And so once again, we have 6, 0 plus 4, 6. This time we're going to multiply by minus 8 over 3 plus 8. All right. And so this first quantity here is just going to be 4. Second quantity here We have a 6 times minus 8/3, and so we multiply that fraction out, that gives us a minus 16. Minus 16 plus positive 8 is just a minus 8. And so multiply these two together, 4 times minus 8 is minus 32. Okay. So the determinant of the first principal submatrix is positive, determinant of the second principal submatrix is negative. Okay, so we're going positive, negative. In this case, this is a point that's semi-definite. And so semi-definite means that we have a saddle point. So that point right there, the derivative is 0 at that point, but it's neither a max nor a min. All right. We have 2 more points to go. I'm going to go a little bit faster with these 2 points because it's kind of just more or less kind of the same thing. Okay. So the third point that we have here is x1 is equal to minus 4/3 and x2 equal to 0. Once again, we're going to evaluate the determinants of the principal submatrices of the Hessian. It's a mouthful. I had to make sure that I said it right. Or it's more that I had to make sure I don't trip over my words, because I feel like my mind goes like, maybe 5 miles an hour faster than my mouth. And so sometimes I can kind of trip over my words. Sometimes if you hear me kind of slow down or kind of eat my words a little bit, that's kind of what's happened. Okay. Once again, let's evaluate A1. Okay. So A1 in this case is it's going to give us minus 4. So that's 6 times a minus 4/3 plus 4. So that's minus 4. And then determinant of A2. Once again, if we plug in, we get minus 32. And so you can see here we have negative, negative. And so in this case, we have also a semi-definite case. You might think that this might be a negative definite, negative, negative there. But remember, to have a negative definite matrix, it was kind of a very kind of strict set of circumstances. And so to get a semi-definite matrix, we need to go negative, positive, negative, positive. So since we have negative, negative, then we have semi-definite. Okay, last point. Okay, so our last point here, we have x1 is equal to minus 4/3. X2 is equal to minus 8/3. Let's evaluate our principal submatrices one more time. A1 in this case is a minus 4. Okay, same as the previous one, because A1 only depends on x1 in this case. And then the determinant of the second principal submatrix, in this case, we get a positive 32. And so since we go negative, positive in this case, this means that our Hessian matrix is negative definite. So if our Hessian matrix is negative definite at a certain location, that means we have a maximum. All right. Any questions on this example here? Okay. All right, so those are the 2 examples that I have for unconstrained multivariable optimization. Okay. So problem 3 in the homework kind of goes over this. Okay, so let's go ahead and move on. We're all done with unconstrained optimization. So now we're about ready to add constraints patterns. Okay, so that took a bit more time than I thought, but we'll see how far we can get into constrained optimization. Okay. So probably for the next at least 3 lectures, and so probably until the end of next week, we'll be talking about constrained classical optimization. Okay? So there's a lot to cover here because once you add constraints to the equation, it does make things quite a bit more complicated. Okay, so before we jump into techniques, let's kind of just remind ourselves what constraints are. So if you recall, from the beginning of class, constraints are basically limitations on the allowable values of our design parameters. Constraints play a very different role from the objective function. And so, for the past week, we've only just been dealing with the objective function, right? Objective function plays the role of rating the performance of your system, right? But constraints, the role they play is just to say that you have your performance, but you can only look for optimal performance in a certain area or under certain constraints. Okay? And so that's that's the role that they play. So of course, this limits kind of the space that we can look for optimal parameters. But oftentimes, these are really important for practical systems. Okay, so remember there are 2 types of constraints. The first type are equality constraints. Right, so equality constraints, these are defined by a mathematical equation with an equal sign. And one way that I'd like to think of equality constraints is that these are hard constraints. And so these are equations that must be satisfied in your own. So oftentimes your equality constraints will be equations that involve more than one design variable. By the way, for everything that we're talking about with constraints, we're going to be working in multivariable situations for the most part. And you'll see why, in a second, please. And remember, standard form for equality constraints is to move everything to one side of the equal sign so that it equals 0. Later on, we're going to go over a technique called Lagrange multipliers, and you'll see why this standard form is actually really important. Okay. All right, so the second type of constraints that we have are inequality constraints. And so in contrast, inequality constraints are defined by an equation with an inequality sign. And so in contrast to equality constraints, for equality constraints, they specify a relationship that must be satisfied. By contrast, inequality constraints, they're more loose, right? They still have to be satisfied, but they instead of a hard relationship, they define kind of an area or a region where valid solutions can be found. And of course, this also has a standard form. Standard form for the inequality constraints is again to kind of move everything to one side of the equal sign, but also to kind of manipulate it so that you have kind of a less than or equal to equality. All right, and so remember the symbol that we had for this is L. The design variables is less than or equal to 0. Okay. And so when you're presented with the problem with constraints, whether they be equality constraints or inequality constraints, you need to factor that into the solution. Okay. And so the methods that we've learned, the classical methods of taking derivatives, we need to modify those methods in order to respect these constraints. Okay. Because if you notice, with our derivative based method, there's no way in that method that we could actually solve, incorporate a constraint into that. We kind of just search wherever that the derivatives are equal. Okay. And so how we incorporate these constraints, there's multiple methods for us to do this. We're going to go over kind of the most common and in my opinion, kind of the easiest way to kind of do these constraints. But these have to be taken into account when you solve for all these functions. All right, any questions on this? Okay, so the first method that we're going to go over is a method for equality constraints. Probably the one that's most intuitive. Probably if I didn't teach you anything, then probably this is probably what you would default to when you see equality constraints. And so the first method that we're going to go over is called direct substitution. Okay. So the method of direct substitution is quite simple. It's very intuitive. Okay. Because equality constraints they basically define a set relationship between the two or three design variables, and there's an equal sign. You can use that constraint and use it to substitute directly into the objective. You can only do this with equality constraints, because equality constraints, remember, is a set relationship, so you can just plug right into it. Okay, and this achieves something, very magical for us, because by directly substituting, what we've basically accomplished is that we've lowered the dimensionality of our objective function. Okay, because by plugging in for a variable, we basically eliminated it from our objective function. And that's huge, right? And so anytime you can eliminate a variable, what that basically means is that it takes down the dimensionality of your problem by 1. Okay, so if you have a 2D two variable optimization with one equality constraint, you can basically plug into that objective function and turn it into a 1D optimization, which is, as we know, a lot easier to handle than a 2-dimensional optimization. Okay, we don't have to do any Hessians or any crazy things. Okay, so let's do a quick example. Kind of illustrate this method here. Okay. So let's consider a 2-dimensional optimization. We have an objective function that's a function of 2 variables, x1, x2. Okay, and we'll do something simple. We'll just say that it's x1 squared minus x2 squared. But we're going to subject this to the following constraints. So we're going to subject it to 4x1 minus x2 equal to 7. Okay. So we want to take this constrained optimization problem and solve for the optimal values of x1 and x2. And so on first blush, right? So we look at this problem, we look at that objective function, and we're like, oh no, here we go again. We got to take, partial derivatives and compute the Hessian and, do all that stuff. But in this case, we're actually saved by our constraint here because it actually makes things a bit easier. Okay? Because what we can do, since we know that our solution here or our optimal values have to satisfy this equation, let's use direct substitution and plug it into our objective function. Okay. So we can use direct substitution either way. So we can either solve this equation for x1 and plug in for x1, or we can solve this equation for x2 and plug in for x2. Okay. Just because x2 is by itself, let's go ahead and do that one. And so if we solve this equation for x2, and so we solve this equation for x2, we get x2 is equal to, so I'm going to add x2 to both sides and then subtract 7. Okay, x2 is equal to 4x1 minus 7. Now let's plug this in for an objective function. Okay. So if we plug into our objective function now becomes a function of just a single variable, x1. We get f of x1 squared minus quantity, or x1 minus 7 squared. Okay. So now what we can do is we can just solve this as a one-dimensional optimization problem, which is leagues easy. Let's take the derivative of f with respect to x1, so we have df dx1 as equal to 2x1 minus 2 times 4 4x1 minus 7. A little bit of chain rule there. So that 2 comes out because of the quantity squared. That 4 comes out there because of the derivative of the inside, 4x1 minus 7. Okay. And then we have the derivative of the outer, which is just 4 x1 minus 7. So yeah. Okay, so we're going to set this equal to 0. Let's divide both sides by 2 just to eliminate that 2 there. Okay, and if we distribute that 4, we get x1 minus 16x1 plus 28. We can solve this for x1. So let's move all the x1 terms over to the other side to get 28 is equal to positive 16x1 minus x1, which is 15x1. And so we solve for x1 in this case. This is 28. All right, so from here, we can now use our constraint to find the value of x2. As we go back to our constraint, we see that x2 is equal to 4x1 minus 7. So let's plug in the value for x1 into here. We get x2 is equal to 4 times 28 divided by 15 minus 7. Okay. Fortunately, we get kind of a gnarly fraction here. And actually, this whole part was kind of off the cuff because I didn't actually finish this equation. I didn't actually finish this example in my notes. Okay. All right, so we'll take it as far as I can. And so we multiply this by 4. 4 times 28 is 112 divided by 15 minus 7. Okay. Right. Let's get this under a common denominator. So let's multiply that 7 by 15 over 15. Okay. Let me just pull out my calculator here, or actually I can do them ahead. So it's 112 over 15. Let's see, 6 times 15 is 90, so 7 times 15 must be 105. Okay. So we have 112 minus 105 over 15, that is 7 over 15. Right, and so that is our optimal, that's our optimal solution there. X1 is equal to 28 over 15, and X2 is equal to 7 over 15. All right, any questions on that? Okay. And of course, another good thing about this is that we can classify this extreme as either a max or min without having to do the Hessian. And so we look back at our objective function, right? And so the derivative of our objective function was this guy up here. Let me go ahead and write that down here again. EF EX1 2 2x1 minus 8 24x1 minus 7. And so just like we did in the one-dimensional case, we just have to take the second order derivative of this with respect to x1. Okay. So let's go ahead and do that. Well, the second order derivative of this is 2 minus, let's see, minus 32. Okay. Because if we distribute that 8, we get a minus 32x1 plus 56. We take the derivative of the 56, it goes away, and the derivative of the minus 32x is just minus 32. And so we evaluate this, of course, we get a minus 30. Okay. And since this is a negative number here, that means our optimal point is a maximum. Optimal point x1 equal to 28 over 15. 2 7 over 15 is a all right. So we took that example, if we apply kind of the same methods that we applied at the beginning of class today, the partial derivatives and Hessians, probably would have taken us another, 25 minutes or so. But we just kind of did that really quickly, and we did it kind of very organically. So if you look at the notes, I didn't have all that there. So we kind of solved this kind of by. All right, any questions on this example here? Okay. All right, so I'm going to start the next example. The next example is actually more interesting, but of course we're not going to finish it in the last 7 minutes. But we'll at least kind of start it. I'll get you guys thinking about it over the weekend, and then we'll finish it up on Tuesday. Okay. So this next example here is something that I've wondered before, just having random thoughts in my brain. And so let's say that you have a sphere. And just for the sake of simplicity, let's say that this sphere has radius of 1 meter. Here. Okay, so perfectly spherical sphere. In this problem, what we're interested in is, let's say that we're designing a box, right? And so what we want to see is that, what are the dimensions of the largest box that we can put inside the sphere without it kind of, bursting or puncturing through the sphere. And when I say largest box, what I mean is the largest box by volume. So it's kind of an interesting situation, right? And so we have kind of a spherical rounded shape, and we're going to put something blocky on the inside, right? And so our blocks It looks something like this. Obviously, I kind of messed up drawing the box, so that box kind of exceeded the sphere. But we want to know what are the dimensions of the box that can do this. Okay. Okay. And so our design variables in this case are going to be the dimensions of the box. So we'll assume that, the length of the box, let's go with the height first. The height of the box is going to be defined by 2x1. Okay. We're sticking with the numbered x's just to kind of, stay consistent with our previous examples. We'll assume that the width of the box, we'll call that 2x2. Okay. And then we'll assume the depth of the box is 2x3. So the reason I'm putting the 2's in front of each of them is that we're assuming that there is an origin right at the middle of this entire thing. We'll assume that there is a Cartesian origin, right here in the middle of the box. And the other thing we're going to assume is that both the sphere and the box are centered on the origin. And so if the box is centered on the origin, and we kind of define the x variables to be kind of the distance between the origin and the extreme of the box, then the length of each side is 2x1, 2x2, 2x3. Okay, so this is our first three-dimensional optimization problem, right? So this is definitely not a trivial problem. Let me just kind of, let's talk about kind of what the objective function is in this case and what our constraint is. Okay. So the thing that we want to maximize in this case is volume. We want to find the largest box by volume that's going to fit inside the sphere. So that tells us that our objective function should therefore be the volume of the box. Okay, so that's the thing that we want to make as big as possible. That's the one we want to optimize. Our constraint and so if that were the case, if our objective function is to find the volume of the biggest box possible, then we would just make the sides of all the boxes infinite, right? So, if a box has sides length infinite, then it's, that's the biggest box ever. But we have a constraint here, right? Our constraint is that our box has to fit inside a sphere of radius 1. All right, and so when we come back on Tuesday, we'll see how this works. Okay, and so of course, we're starting with three-dimensional optimization, but we do have a constraint here, and if we treat that as an equality constraint and we use our direct substitution method, we can actually transform this into a 2D optimization, save ourselves a ton of time. All right, so thank you guys for coming today. Hope you guys have a good rest of your day. Hope you guys have a good weekend, and I'll see you guys on Tuesday.
Say something like yeah, so that's really started. Yeah. My research. You don't have a solid foundation. I can.